Okay, hi everyone, welcome back to this video series on Windows Server 2012. Introducing DNS. The domain name system DNS is a service that allows you to resolve a host name to an internet protocol IP address. One of the inherent complexities of operating in networked environments is working with multiple protocols and network addresses. Owing largely to the tremendous amount in the popularity of the internet, however, most environments have transitioned to use transmission control protocol, internet protocol, TCP/IP as their primary networking protocol. Microsoft is no exception when it comes to supporting TCP/IP in its workstation and server products. All current versions of Microsoft's operating systems support TCP/IP, as do most other modern operating systems. An easy way to understand DNS is to think about making a telephone call. If you wanted to call Microsoft and did not know the number, you could call information and tell them the name Microsoft and get the telephone number. You would then make the call. Now think about trying to connect to server 1. You don't know the TCP/IP number, the computer's telephone number. So you ask your computer asks DNS information for the number of server 1. DNS returns the number, and your system makes the connection call. DNS is your network's 411 or information, and it returns the TCP/IP data for your network. TCP is actually a collection of different technologies that allow computers to function together on a single, large, and heterogeneous network. Some of the major advantages of this protocol include widespread support of hardware, software, and network devices, reliance on a system of standards, and scalability. TCP handles tasks such as sequenced acknowledgements. IP involves many jobs such as logical, subnet, assignment, and routing. The form of an IP address. To understand DNS, you must first understand how TCP/IP addresses are formed, because DNS is strictly on a network to support TCP/IP. Understanding the basics of TCP/IP is extremely important. An IP address is a logical number that uniquely identifies a computer on a TCP/IP network. TCP/IP allows a computer packet to reach the correct host. Windows Server 2012 R2 works with two versions of TCP/IP, IPv4 and IPv6. IPv4 address takes the form of 4 octets, 8 binary bits, each of which is represented by a decimal number between 0 and 255. The 4 numbers are separated by a decimal point. For example, all of the following are valid IP addresses: 128.45.23.17, 230.212.43.100.10.1.1.1. The dotted decimal notation was created to make it easier for users to deal with IP addresses, but this idea did not go far enough. As a result, another abstraction layer was developed, which used names to represent the dotted decimal notation, the domain name. For example, the IP address 110.0.0.0.0.0.0.0.0.0.0.0.0.1 maps to 192.168.1.21, which in turn might map to server1.company.org, which is how the computer's address is usually presented to the user or application. As stated earlier, IPv4 addresses are made up of octets, or the decimal base 10 representation of 8 bits. It takes 4 octets to add up to the 32 bits required. IPv6 expands the address space to 128 bits. The address is usually represented in hexadecimal notation as follows: 2001:0, capital D, capital B, 8:00:00:00:00:00:12345:0 capital A 9, capital F, capital E, 133, capital E. You can tell that the implementation of DNS would make life a lot easier for everyone, even those of us who like to use alphanumeric values. For example, some of us enjoy pinging the address in lieu of the name. Fortunately, DNS already has the ability to handle IPv6 addresses using using an AAAA record. An A record in IPv4's addressing space is 32 bits, and an AAA record, 4 A's in IPv6 is 128 bits. Nowadays, most computer users are quite familiar with navigating to DNS-based resources such as www.microsoft.com to resolve these friendly names to TCP IP addresses at the network that the network stack can use. You need a method for mapping them. Originally, ASCII flat sites, often called host files, as shown in figure 2.1, were used for this purpose. In some cases, they are still used today in small networks and can be useful in helping to troubleshoot name resolution problems. As the number of machines and network devices grew, it became unwieldy for administrators to manage all of the manual updates required to enter new mappings to a master host file and distribute it. Clearly, a better system was needed. As you can see from the sample hosts file in figure 2.1, you can conduct a quick test of the email server's name resolution as follows. Open the host file, c:/system32/drivers/etc2. Add the IP address to host mapping. 3. Try to ping the server using the host name to verify that you can reach it using an easy to remember name. Following these steps should drive home the concept of DNS for you, because you can see it working to make your life easier. Now you don't have to remember 10.0.0.10, only need to remember exchange 03. However, you can also see how this method can become unwieldy if you have many hosts that want to use easy to remember names instead of IP addresses to locate resources on your network. When dealing with large networks, users and network administrators must be able to locate resources they require with minimum searching. Users don't care about the actual physical or logical network addresses of the machine. They just want to be able to connect to it using a simple name that they can remember. From a network administrator's standpoint, however, each machine must have its own logical address that makes it part of the network on which it resides. Therefore, some scalable and easy to manage method for resolving a machine's logical name to an IP address and then to a domain name is required. DNS was created just for this purpose. DNS is a hierarchical distributed database. In other words, its layers are arranged in a definite order, and its data is distributed across a wide range of machines, each of which can exert control over a portion of the database. DNS is a standard set of protocols that defines the following: a mechanism for querying and updating address information in the database, a mechanism for replicating the information in the database among servers, a schema of the database. DNS was originally developed in the early days of the internet, called ARPANET at the times, when it was a small network created by the Department of Defense for research purposes. Before DNS, computer names or host names were manually entered into a host file located on a centrally administered server. Each site that needed to resolve host names outside of its organization had to download the file, and the number of computers on the internet grew, so did the size of the host file, and along with it, the problems of its management. The need for a new system that would offer features such as scalability, decentralized administration, and support for various data types became more and more obvious. DNS, introduced in 1984, became this new name. With DNS, the host names reside in a database that can be distributed among multiple servers, decreasing the load on any one server and providing the availability to administer this naming system on a per partition basis. DNS supports hierarchical names and allows for the registration of various data types in addition to the host name to IP address mapping used in host files. Database performance is ensured through its distributed name as well as through caching. The DNS distributed database establishes an inverted logical tree structure called the domain namespace. Each node or domain in that space has a unique name. At the top of the tree is the root. This may not sound quite right, which is why the DNS hierarchical model is described as being an inverted tree with the root at the top. The root is represented by the null set. When written, the root node is represented by a single dot. Each node in the DNS can branch out to any number of nodes below it. For example, below the root node are a number of other nodes, commonly referred to as a top-level domains, TLDs. These are the familiar .com, .net, .org, .gov, .edu, and other such names. Table 2.1 lists the names of these TLDs. Common level domains. I just increase the size there. So common top level domains type of organization. Commercial, for example, Stellacom for Stellacom Training Corporation. Edu, educational, for example, gatech.edu for the Georgia Institute of Technology. Government, for example, whitehouse.gov for the White House, Washington, D.C. INT, international organization, for example, NATO.int for NATO. This top-level domain is fairly rare. Military organization, for example, USMC.mil for the Marine Corps. There is a set of root name servers for this domain. Networking organizations and internet providers, for example, highway.net or highway information systems. Many commercial organizations have registered names under this domain too. Org. Non-commercial organization, for example, fidonet.org for FidoNet. AU, Australia, UK, United Kingdom, CA, Canada, United States, JP, Japan. Okay, each of those nodes then branches out into the other set of domains, and they combine to form what we refer to as domain names, such as Microsoft.com. A domain name identifies the domain's position in the logical DNS hierarchy in relation to its parent domain by separating each branch of the tree with a dot. Figure 2.2 shows a few of the top level domains where the Microsoft domain fits and a host called Tiger within the Microsoft.com domain. If someone wanted to contact the host, they would use the fully qualified domain name fqdn tiger.microsoft.com. FQDN includes the trailing dot to indicate the root node, but it's commonly left off in practice. As previously stated, one of the strengths of DNS is the ability to delegate control over portions of the DNS namespace to multiple organizations. For example, the Internet Corporation for Assigned Names and Numbers, ICANN, assigns control over TLDs to one or more organizations. In turn, those organizations delegate portions of the DNS namespace to other organizations. For example, when you register a domain name, let's call it example.com, you control the DNS for the portion of the DNS namespace within example.com. The register controlling the .com TLD has delegated control over the example.com node in the DNS tree. No other node can be named example directly below the .com within the DNS database. Within the portion of the domain namespace that you control, example.com, you could create a host and other records. More of these later. You could also further subdivide example.com and delegate control over those divisions to other organizations and departments. These divisions are called subdomains. For example, you might create subdomains named for the cities in which the company branch offices, and then delegate control over those subdomains to the branch offices. The subdomains might be named Los Angeles .example.com, Chicago.example.com, Portsmouth.example.com, and so on. Each domain or delegated subdomain is associated with DNS name servers. In other words, for every node in the DNS, one or more servers can give an authoritative answer to queries about the domain. At the root of the domain namespace are the root servers. More on these later. Understanding servers, clients, and resolvers. You will need to know a few terms and concepts in order to manage a DNS server. Understanding these terms will make it easier to understand how the Windows Server 2012 R2 DNS works. DNS server. Any computer providing domain name services is a DNS name server. No matter where the server resides in the DNS namespace, it's still a DNS name server. For example, 13 root name servers at the top of the DNS tree are responsible for delegating the TLDs. The root servers provide referrals to name servers for the TLDs, which in turn provide referrals to an authoritative name server for a given domain. Any DNS server implementing, supporting service, locating resource records and dynamic updates is sufficient to provide name servers for any operating system running Windows 2003 software and newer. DNS client. A DNS client is any machine that issues queries to a DNS server. The client host name may or may not be registered in a DNS database. Clients issue DNS requests through a process called resolvers. You'll sometimes see the terms client and resolver used synonymously. Resolvers are software processes, sometimes implementing the software libraries that handle the actual process of finding the answers to queries for DNS data. The resolver is also built into many large pieces of software so that external libraries don't have to be called to make the process and DNS queries. Resolvers can be what you'd consider client computers or other DNS servers attempting to resolve an answer on behalf of a client, for example, Internet Explorer query. A query is a request for information sent to a DNS server. Three types of queries can be made to a DNS server: recursive, inverse, and iterative. I'll discuss the difference between these queries in the section DNS queries a bit later in the chapter, understanding the DNS process. To help you understand the DNS process, I will start by covering the difference between dynamic DNS and non-dynamic DNS. During this discussion, you will learn how dynamic DNS populates the DNS database. You will also see how to implement security for dynamic DNS, and I will then talk about the workings and differences and different types of DNS queries. Finally, I will discuss caching and time to live TTL, dynamic DNS and non-dynamic DNS. To understand dynamic DNS and non-dynamic DNS, you must go back in time. Here is where the TV screen always used to get wavy. Many years ago, when many of us worked on Windows NT 3.51 and Windows NT 4.0, almost all Microsoft networks used Windows Internet Name Services, WINS, to do their TCP IP name resolution. Windows versions 95, 98, and NT 4.0 Professional were all built with the idea of using WINS. This worked out well for administrators because WINS was dynamic, which meant that once it was installed, it automatically built its own database. Back then, there was no such thing as dynamic DNS. Administrators had to enter DNS records into the server manually. This is important to know even today. If you have clients still running any of these older operating systems, 95, 98, and NT4, these clients cannot use dynamic DNS. Now let's move forward in time to the release of Windows Server 2000. Microsoft announced that DNS was going to be the name resolution method of choice. Many administrators, myself included, did not look forward to the switch because there was no such thing as dynamic DNS. Most administrators had nightmares about manually entering records. However, luckily for us, when Microsoft released Windows Server 2000, DNS had the ability to operate dynamically. Now, when you're setting up Windows Server 2012 or to DNS, you can choose what type of dynamic update you would like to use, if any. Let's talk about why you would want to choose over the one over the other. That the dynamic DNS DNS standard described in RFC 2136 allows DNS clients to update information in the DNS database files. For example, Windows Server 2012 or to DHCP server can automatically tell a DNS server which IP address it has assigned to what machines. Windows 2000, 2003, 2008, XP Pro, Vista, Windows 7, and Windows 8 DHCP clients can do this too. For a security reason, however, it is better to let DHCP server do it. The result, IP addresses and DNS records stay in sync so that they can use DNS and DHCP together simultaneously. Because DNS is a proposed internet standard, you can even use Windows Server 2012 or to DNS aware parts with Unix, Linux-based DNS servers. Non-dynamic DNS NDDNS does not automatically populate the DNS database. The client systems do not have the ability to update DNS. If you decide to use non-dynamic DNS, an administrator will need to populate the DNS database manually. Non-dynamic DNS is a reasonable choice if your organization is small to mid-sized and you do not want extra network traffic clients updating to the DNS server, or if you need to enter the computer's TCP/IP information manually because of the strict security measures. The major downside to entering records into DNS manually occur when the organization is using the dynamic host configuration protocol, DHCP. When using DHCP, it is possible for users to end up with different TCP/IP addresses every day. This means an administrator has to update DNS manually each day to keep it accurate. If you choose to allow dynamic DNS, you need to decide how you want to set it up. When setting up dynamic updates on your DNS server, you have three choices. See figure 2.3. None. This means your DNS server is non-dynamic. Non and secure. This means that any machine, even if it does not have a domain account, can register with DNS. Using this setting could allow rogue systems to enter records into your DNS server. Secure only. This means that only machines with accounts in Active Directory can register with DNS. Before DNS registers any account in its database, it checks Active Directory to make sure that the account is an authorized domain computer. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing, and subscribing. Thank you.